I'm delighted to be here, meet old friends, see new friends. And my disclosure, I'm a co-founder of Osmol Therapeutics, which is doing work related to what I'm going to discuss today. And since you haven't heard anything about, other than my questions about intracellular calcium channels, I want to point out this is my very limited view about a cell. You have these receptors on the outside linked to PLC, and there's a PIP2, which is actually in the wrong place. It's in the membrane, and when it's cleaved, it makes IP3, and it turns on the IP3 receptor, and calcium is high inside the endoplasmic reticulum, low in this blue C of the cytoplasm, and high out here. And basically, we're interested in what happens inside here. And this was an old version, but now we need to include my now new favorite protein, neuronal calcium sensor 1. Okay, so this is the outline. We're going to talk about the players in calcium signaling that I'm going to talk about, then how this interaction initiates side effects of chemotherapy, and then how to prevent those side effects. Okay, so it's going to be the IP3 receptor and neuronal calcium sensor 1. IP3 receptor, this is the cryo-EM, so the transmembrane part is around here. So most of the protein is out in the cytoplasm. It is a very beautiful, it's one of the largest protein structures. It's about 1 million Daltons. So it's a tetramer of 250,000 Daltons. So it's about 1 million Daltons. And then you already heard me say something about Purkinje cells of the cerebellum. This is a stain of an antibody stain of a slice through the cerebellum. And you can see that these nice, it's called a necklace of Purkinje cells. These are stained with IP3 receptor. And there's more IP3 receptor in these cells than any other known type. It's not clear why, but for biochemistry and other processes, it's been great for studying. And this IP3 receptor is regulated by a lot of things. And one of the things it's regulated by is calcium. So this is looking at the open probability as a function of the calcium concentration, and resting calcium is around here. And in the presence of IP3, as you increase the calcium, you get a positive amplification. And at some point, and this is a 0.3 micromolar cytoplasmic calcium, you get a turning off. So this is a protein that has both a positive and a negative amplification. And this is exactly what you need for oscillations, which I'm not going to talk about at all today, but a topic I'm passionately interested in, so we can talk about it another time. Neuronal calcium sensor 1 is a member of the calcium sensor proteins. Most people have heard of calmodulin. So this is the calcium. This is looking at calcium bound. Calmodulin is in the middle. NCS1 is over here with the KD, again, near the resting calcium level. So this is proteins important for maintaining calcium homeostasis. We know a lot about this protein. It's been crystallized. I think of it like a hot dog bun. And then there's a hydrophobic pocket down the middle, and that's where a lot of things bind. So drugs bind there, proteins bind there. So that's where IP3 receptors bind. So this is how a molecular biologist thinks of the IP3 receptor. This green part is where IP3 binds. This orange part is what's called the suppressor domain. This is regulatory, and this gray here is the transmembrane region. And to cut to the chase, NCS1 binds in this suppressor domain. Okay, it binds, but big deal. We know exactly which amino acid on IP3 receptor. We know exactly which amino acids are important in the NCS1. So in NCS1, you'll have to remember L89. There's a functional effect. So this is looking at the IP3 receptor in a planar lipid bilayer. We do IP3 receptors in planar lipid bilayers because it's an intracellular membrane protein. You can't use a patch clamp. You have to isolate the protein and put it in an artificial membrane. So here, the IP3 receptor, IP3 has been added, and you get this opening, pretty pathetic, of 4%. That's the best we could do at the highest IP3 concentration. But then look what happens. When you add NCS1 to the cytoplasmic side, all of a sudden you can get the channel to be open about 1/4 of the time. NCS1 alone won't open the channel. It needs the IP3 present. And if you have an NCS1 that's been mutated so it doesn't bind calcium, it doesn't work either. So you need calcium, IP3, and NCS1. Okay, this is 2 proteins in a cuvette looking at the electrical properties. What about in a cell? Sure enough, so this is now, we've done it in a variety of different cell types. This is a neuroblastoma cell type. This is time on the x-axis, and this is the calcium magnitude in the cytoplasm. And where the higher the number, the higher amount of calcium inside the cell. You add, here we added UTP, it doesn't matter. I don't care about the agonist. I just care that we turn on IP3 production. And the blue curve here is a regular control. If you overexpress NCS1, you get more, just as you'd expect because you're opening the channel more. If you add this mutant E120Q, which didn't open it, you don't get activity. And L89A, so if you mutate the binding site so IP3 receptor and NCS1 don't bind, you don't get the effect. Okay, so it works in the cell. That's all I'm going to tell you about these 2 proteins. We know a lot more, but that's all I'm going to show you today. I'm just going to tell you that this protein regulates the IP3 receptor. It binds other proteins. I'm not going to talk about the other proteins. Just know that we're only going to talk about this today. Okay, it has effects on chemotherapy. You've already heard a lot about paclitaxel. Paclitaxel is a wonderful drug. Well, terrible actually, but it stabilizes microtubules and it works to treat lots of tumors, but it has side effects. It causes peripheral neuropathy, actually I'm not allowed to call it this anymore, I have to change this. NIH says I have to call it chemotherapy-induced cognitive impairment, but it's basically a chemophage. About 80% of the people who get treated with paclitaxel get peripheral neuropathy and chemobrain, and half of those it never reverses. So and there's no treatment whatsoever. So it's a real impairment. And so for example, you think of a breast cancer patient who can be essentially cured. They live 20 to 40 years after they get treated. They have neuropathy and brain fog for the rest of their life. We think that this happens, the side effect is initiated by the interaction between paclitaxel and NCS1. We've shown that NCS1 binds paclitaxel by phage display, by NMR, by tryptophan fluorescence. So what happens is if you add paclitaxel here, you get these calcium oscillations, the black curve. If you have NCS1 knockout, or you remove NCS1, you do not get this effect. Here we added thapsigargan, which opens that blocks the calcium ATPase, so it shows that there was calcium. You could have gotten calcium signaling, but without NCS1, there's no binding of paclitaxel. You don't get a dump of calcium. And so I'm going to go from looking at the cell all the way up to a mouse. So how do you know if a mouse has peripheral neuropathy? Well, we use a technique called a rotarod, which is putting a mouse on a rotating rod like a log roll, and they get better with time. So it's a mixed assay. They have sensory, motor, and cognitive. We know from other experiments there's no effect sensory, no effect motor, but here, this is a knockout mouse, and this is exactly what an untreated mouse looks like. But here's a knockout mouse that is treated with paclitaxel, and they learn over time, and they stay on the rotating rod. Whereas if you take a wild-type mouse, treat them with paclitaxel, they basically fall off the rotor rod too fast, and they never learn. So this is how you tell that they have neuropathy. What do we think is happening? So we think that paclitaxel is binding to NCS1. NCS1 then, the combination is binding to the IP3 receptor, getting a dump of calcium from the endoplasmic reticulum through the IP3 receptor, turning on calpain, which is a calcium-activated protease, and then you chew up a bunch of things, among them NCS1. And here it shows you, this is a Western blot, there's a vehicle, and then we lose most of the Taxol. So you would predict, I already showed you, if you have more NCS1, you get more calcium. If you have less NCS1, you get less calcium release, and so that's exactly what's shown here. This is time. This is calcium in the cytoplasm. This is, again, neuroblastoma cells. We added ATP here. It doesn't matter what we used to make IP3. And here's a wild type calcium transient. This is after treatment with 6 hours with paclitaxel. This is about 1 micromolar, which is about the level that you find in a patient that's treated with breast cancer patient treated with paclitaxel. So what happens in the CNS? And I'm just giving you the highlights here. In a knockout mouse, a mouse that's lacking NCS1, you get pruning of the dendritic arbor. So here, this is a spina lucida of these Golgi stains. This is a wild type. This is a NCS1 knockout. And this is looking using Scholl analysis. You can see that there's less complexity in the NCS1 knockout than in the wild type. So you have cognitive effects and you have peripheral effects. How do we know? How are we sure that it's through this pathway of calpain? Well, what we showed is that this is, again, neuroblastoma cells in a dish. This is a wild type cell. The dotted curve here is a Taxol-treated cell, and you get a diminished calcium. But if you use calpastatin, which is a endogenous antagonist of calpain, you no longer get the loss of the calcium signaling. So you're maintaining calcium normally. So what we think is happening, paclitaxel and NCS1 bind to the IP3 receptor, you get a calcium dump that turns on calpain, and that calpain then takes a bunch of proteins, including NCS1, and degrades them, and it's that loss of proteins that causes the loss of function of the neurons. Okay, so that's what I just showed you. So this is our mechanism. We've looked at a lot of these. We can show that we turn on calpain. We can show that we've lost NCS1. We show that we have calcium release. Okay, so now I'm going to talk about the side effects that we can prevent them. Okay, how are you going to prevent it? Well, one possibility is to make it so paclitaxel doesn't bind to NCS1. You can't, having my limited experience of dealing with the FDA, there's no way you're going to get another poison approved by the FDA at this time. So that's out. Another possibility is obvious would be to use calpain antagonist. And many people have used antagonists of calpain for neurodegeneration and prevent. And it turns out that the side effects of calpain antagonism is worse than having the disease itself, because calpain's everywhere. You need calpain, so that's out. So we have to think about the binding between NCS1 and the IP3 receptor and the calcium dump. So we are presently working on this interaction. And because we know the exact location of the binding, we've made a peptide that we made membrane permeate. We can have this membrane permeate peptide incubate with the cells, and we can diminish the interaction between the IP3 receptor and NCS1. So now that we have a peptide, we know with a gifted medicinal chemist, we will be able to make a small peptide, but that's a promissory note. You'll have to wait till probably 2 years from now. Okay. We did not do a search. When we were first looking at the effects of NCS1 on the IP3 receptor, before we knew anything about paclitaxel, my student, Christina here, said she didn't want her paper to go just into Journal of Something. She wanted to go into Journal of Something, right? And so I said, well, find out some clinical correlation about NCS1. And she did. Back then, she went to the library, and she found that NCS1 was elevated in bipolar patients. And I said, gee, that's interesting, because my PhD was on lithium treatment of bipolar patients. And I said, ha, 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 try lithium. it works. So here is the activity of the IP3 receptor by itself. Here's the activity of IP3 receptor with NCS1. If you add lithium to the non-NCS1, nothing happens. So lithium has no effect on the IP3 receptor by itself. But in the presence of NCS1, you bring it back down to as if NCS1 wasn't present. So it's a modulator of the modulator. It's not an inhibitor, not a classic, it's a modulator of a modulator. So I already showed you that chronic paclitaxel reduces NCS1, that's shown here, but now I can tell you that if you pre-treat the cells with lithium at levels that are used to treat bipolar patients, you can preserve the level of NCS1. It has no effect. That's in cells. Then if we did this, we've done this in cells, this is DRG neurons taken from mice that were treated with paclitaxel. And this is 4 weeks after the last injection of paclitaxel. So this is the calcium transient. The black curve is the wild type untreated, essentially. Red curve here is what happens in the DRG neurons that were treated with paclitaxel only. So you get, even 4 weeks after the last dose, you still have loss of calcium signaling. If you have either lithium alone or paclitaxel plus lithium, you can preserve most of the signaling. Okay, that's in a dish, that's a cell. What about in a mouse? How do you tell, like I said, how do you tell if a mouse has peripheral neuropathy? I already showed you. We did this where we gave lithium chloride and paclitaxel 4 injections every other day for a week. We did open field and displayed object recognition. That's for the cognitive. We did rotarod. At the end, we killed the mice. Sure enough, here is, again, the paclitaxel in a wild-type mouse, and you see that they don't stay on the rotarod. They don't really learn. But if you pre-treat with lithium, with paclitaxel, this looks just like a wild-type mouse. We can prevent the occurrence of the peripheral neuropathy in these mice. Okay, this is a mixed assay. I already told you. We know it's not motor. So what we did was we did nerve conduction in the tail of a mouse. So this way we get a pure sensory effect. And this drooping curve is the paclitaxel only. This is looking at this sensory nerve action potential amplitude. So we get a droop, whereas if we have control, lithium or paclitaxel with lithium, we don't have the effect. To say that this is related to how you have neuropathy, and these are not my data, these are from the literature. Grade 1, grade 2, grade 3 in neuropathy, where grade 3 is the most severe. And this is the same measurement, the sensory nerve action potential, and you get a decrease in the sensory nerve amplitude just like here. So this shows that we have the same effect. I'm not showing you all the cognitive things, how we measure the cognitive. I'm just showing you that in the paclitaxel-treated mice, which is this orange curve here, just like in the NCS1 knockout, we get a loss of the dendritic complexity that is prevented by the addition of lithium. You can also see in the spine density, these are the control. This is lithium only. This is paclitaxel treated. You can see there's fewer spines, and this is in the lithium pre-treated. And truth of advertising, my student and I had an argument about this figure because it looks like there's more spines. She loved this figure. If you look at the statistics, there's no difference between the lithium and taxane than the control. So every now and then you have to let your students win. Okay, this is all great. We can prevent, but what happens to the ability to shrink the tumors? And I'm happy to say there's absolutely no effect on the ability to shrink the tumors. We did the experiments in our lab, but pharma doesn't believe people like me who have a skin in the game. So luckily, the Yale Cancer Center gave the money to let Charles River repeat our experiments. And what you see here is you give a mouse a tumor And after 30 days, if you don't treat them, the tumor gets so large you have to sacrifice the mouse. But if you pre-treat them with lithium, there's no difference in the ability to shrink the tumors. And that's shown that lithium alone doesn't make the tumors larger, and it doesn't inhibit the ability to shrink the tumors. Okay, lithium's a repurposed drug. It's used to treat bipolar disease. I told you that something that we studied a long time ago. What about a retrospective chart review? Okay, this is a very simple concept. It took us 3 years to get this crummy number of patients. Okay, we found at the West Haven VA, we had, so this is men with prostate cancer. Patients without mood stabilizer, 110, 40% had new peripheral neuropathy. We deleted everybody who had diabetic neuropathy. And we believe this is an underreporting because people don't often complain about the neuropathy. We found 4 bipolar patients that were treated. None of them had peripheral neuropathy. This is way too low to be statistically significant, but it's the right direction, okay? And my colleague who started some of this project is a neurologist now, has some off-label patients that he's been treating, and they also don't have neuropathy, so we're optimistic. All right, so we now think that if you add lithium, you block this dump of calcium. If you block the dump of calcium, don't turn calpain on, don't inhibit or you don't lose any of these proteins, and you don't lose the integrity of the neuron. This mechanism is upstream of almost all the other mechanisms that have been proposed. For example, it's thought that there's mitochondrial dysfunction. Well, that's because there's calcium overload. Of course there's calcium overload because you get too much calcium. It's also, I showed you that NCS1 binds to membrane proteins than plasma membrane. Yes, there's effects there. It's not the initial effect. The initial effect is this one, and we can obliterate all the other downstream effects by blocking the dump. Okay, how many people have ever had 7-Up? 7-Up is a lithiated soda. Was, just like Coca-Cola doesn't have cocaine anymore, 7-Up doesn't have lithium anymore. 7 is from the molecular mass of lithium. Up is because it's a mood lifter. You can see here it says, takes the ouch out of grouch. All right, so summary. We think that chemotherapy induces change in neurons, and we can prevent it. We believe it's through this NCS1 pathway. We think there are useful effects of this low dose. Essentially, it's a low dose. You only have to have the lithium on board when the paclitaxel. So for a breast cancer patient who gets paclitaxel once a week, you need 1 injection of lithium. So you get about 10 times less lithium than a bipolar patient. So paclitaxel binding to NCS1 makes hyperactive calcium signaling, decreases the effect of paclitaxel on functions, and maintains intracellular signaling. Okay, what's next? Well, I have to add lithium. What are the precise, we don't know exactly what's happening, okay? That's one of the things we're interested in, exactly how, what's really happening to make the neuropathy in chemo brain. We think it might be we're starting this road to look at other forms of neuropathy, looking at better drugs for chemo and neuropathy. We think it's linked to other, NCS1 is linked to other pathologies. Those who were at the Yale meeting, we had Wolfram syndrome is also related to NCS1. And just so you know, there's a clinical trial in patients in the planning. Hopefully, if we raise the money, it'll be happening in mid-24. And of course, I have my wonderful collaborators. I'll stop.
Thank you very much, Barbara. Do we have time? Well, we have time for a couple of quick questions. Are there any out there? Yes. Thank you.
Great talk, Barbara. Thank you very much. So just about your calcium overload phenomenon, the coupling to calpain. So you showed that paclitaxel induced calcium oscillations in the neuroblastoma cells, and a lot of people would argue that that's not really that much calcium overload. The kinetics look quite nice, sharp uprise, you know, multiphasic recovery. The cells look pretty happy with regards to calcium homeostasis. So what's special about the NCS1 paclitaxel complex activating IP3 receptors that then makes calpain so sensitive to that? Because that wouldn't be an output of a lot of metabotropic activation. So what's...
We think it's a pretty big dump at first. So first of all, I think it's
Okay.
pretty big, and I don't think calpain's turned on that long. And I'll just say, truth in advertising, one of the things that I'm happy if anyone has any ideas, because I showed you that 4 weeks after the last dose, there's still a diminished calcium response. And so there's something that happens that makes it irreversible. So there's something special, and I don't know the answer to that yet.
Yes, one last question here.
Just a really quick question. I'm pretty ignorant of the field, but I understand these receptors can cluster.
Which receptors?
The IP3 receptors cluster.
Yeah?
So do you think that's having an impact, if that's where the calcium is from? And would that offer a new opportunity to disrupt this IP3-driven release and reverse some of the effects you're seeing?
Absolutely. I mean, anything that causes a less of a calcium dump is from our point of view, because we can definitely see that there's calcium dump and then there's a loss of proteins. We know if we block calpain, we don't lose the proteins, we don't change the function.
Excellent. So thank you very much, Barbara.